Hi everyone, welcome to Module 2, Foundations for Testers. In this module, we will build the core concepts that testers need to understand when working with AI and machine learning systems. The goal is not to make everyone a data scientist, but to give you enough practical knowledge to test these systems confidently, understand their risks, and communicate effectively with technical teams. This module is divided into 4 parts. We will begin with key machine learning concepts for testers, then move on into NPL foundations so you can understand how language models process text. After that, we will cover prompt engineering and how testers can use prompts to guide AI behavior more effectively. Finally, we will look at responsible AI, including fairness, safety, privacy, and governance considerations that should be part of QA practice. Section 1, Key ML Concepts for Testers. This first section focuses on practical machine learning concepts explained from a QA perspective. As testers, we don't need to build models ourselves, but we do need to understand what model is doing, what can go wrong, and how to test behavior that is probabilistic rather than strictly deterministic. This section gives us the vocabulary and structure we will use throughout the rest of the module. So what is machine learning? Machine learning is a system that learns patterns from data rather than relying on a hard-coded rules. Instead of explicitly programming every output, we train the model using examples and let it discover useful structure in the data. That means output can vary and may not always be identical for similar inputs, which is very different from traditional software. For testers, this means we need to think in terms of data quality, training behavior, and threshold-based assertions instead of only exact expected output. ML workflow overview. So this slide introduces the basic ML workflow: data, model, training, and inference. Data is the raw input the system learns from. The model is the mathematical structure that captures patterns. Training is the learning process, and inference is the stage where the trained model makes predictions on new inputs. For testers, this 4-part workflow is useful because it gives us a framework for organizing our testing approach. We can test each stage separately and also verify how they interact end to end. Data is the foundation of any machine learning. Features are the input variables the model uses. Labels are the expected outcomes. And train, validation, and test splits help evaluate the model fairly without leakage. If the data is poor quality, incomplete, or unrepresentative, the model will inherit those weaknesses. From a tester's perspective, key checks include data formatting, missing value handling, edge case coverage, and whether the data distribution reveals imbalance or bias. Models come in different forms depending on the problem they solve. Classification models predict categories, regression models predict numerical values, sequence models handle ordered inputs, and transformer power many modern large language applications. Testers need to understand the type of model they are dealing with because that affects what correct behavior looks like. For QA, important focus area include testing input-output relationships, checking boundary behavior, and watching for drift in model performance over time. Component C, training, the learning process. Training is the process where raw data is prepared, transformed, and used to teach the model patterns. The typical sequence is raw data, pre-processing, training, and then evaluation. Each of these stages can introduce issues, so testing should not start only after the model is deployed. Testers should verify pre-processing logic, look for signs of overfitting, and where possible, support unit testing for training pipelines so that changes in data or code do not silently degrade model quality. Component D, inference, post-deployment testing. Inference is what happens after deployment when the system receives a request, runs the model, and returns a prediction or a response. In many applications, this happens through an API flow from server to model to prediction and then back to the client. Testing here includes traditional checks like response codes and API contract validations, but also AI-specific concerns such as latency, stability under load, and how the model behaves when it receives unusual or out-of-distribution inputs. This is where the production behavior becomes especially important. ML testing versus functional testing. This slide highlights a major difference between traditional functional testing and ML testing. Functional systems are usually deterministic with exact expected outputs, while ML systems are probabilistic and data-driven. Instead of only checking logic, bugs, or UI issues, AI testers also need to consider biases, drift, hallucinations, and statistical performance. So the testing mindset shifts from exact assertions to threshold-based evaluation and distribution-aware reasoning. Let's get into the hands-on exercise as a part of ML testing learning. This exercise is designed to help you think like an AI tester. The prompt asks for ML-specific test scenarios for a fraud detection model, including data drift, class imbalance, and edge cases. The goal is to compare those scenarios with traditional functional test cases and see how the focus changes. In functional testing, we usually emphasize business rules and logic path. In ML testing, we add concerns like threshold, biases, and shifting data behavior over time.